Thank you. Right. So, okay, today we're going to talk about something that we have not encountered before. So it's essential to Bayesian methods to machine learning, and we are only spending essentially one session in this vast topic to give you a taste. I would say that, well, the design of the selection of content means that we're not going to have space to go into detail of this section. One thing that we can take away from this is that once you learned sampling, it helps us to think about many of the different difficult inference problems in graphical models, which will come next. And in defense of why we're covering sampling before graphical models, which is like the reverse of the work what the book does, I think there are both, like, we think about sampling right now as a prerequisite to understanding the full gamut of problems and tools that we can use in graphical models. Of course, as you go deeper in both topics, they are tightly sort of integral to each other. Because the other alternative is we have essentially 5 sessions in graphical models, like the generic and then the 2 sequentials. Covering sampling the last is not necessarily good either. So let's delve into it and give ourselves a taste about what sampling is. Just as a brief note, I'm happy to talk about like the video assignment that was just released, and give people some guidance and ideas about what are good and bad videos, or what are some tips about what to cover and how to cover things in videos. So stay tuned of the recording or the Q&A session afterwards. So sampling is a really old topic. It's as old as people started to think about random phenomena in nature. And it actually helps on some long-running, very difficult problems, such as estimating pi. So what's summarized in this one slide is this method called Buffon's needles from 1777, right? So from the 1700s. So how does one estimate the quantity, the elusive quantity pi, which is an irrational number, right? Let's see, right? So we know that, okay, so let's say, here's one naive method, right? If I have a circle of, say, okay, I'm not drawing this inscribing circle very nicely. Anyway, so here's the idea, right? So the naive method will have essentially a circle of r equal to 1. And then let's say we randomly put points inside a square where the length of the sides is equal to 2, right? So pi r squared, like over 4 is, or over 2 squared, is the probability that these dots fall inside the circle, which will in turn gives us an estimate of pi. So that's nice, right? The difficulty comes from the fact that, well, before the age of computers, simulating dots is really hard. And also judging whether dots is exactly inside or outside of the circle. So there is no dots of 0 radius, so to speak, right? So Buffon's needle is this clever trick. where this slide draws one set of lines, but in reality, you can think about essentially a large set of parallel lines, and then where the distance of each is all d, and then you can essentially take a whole bunch of needles. Just imagine a whole box of needles or push pins, and then you just put it on the sheet of paper with many of these parallel lines. Suppose now we're dealing with a simple case where the length of the needle, here we assume C is less than D, or equal than D. Then we ask, what is the probability of each needle intersecting with the line, right? So let's say each needle is like this, and then some other needle will fall like this, and so on. So from simple trigonometry, you can see that if the needle is perpendicular to the lines, then the probability of them crossing the line is C over D, right? So if we move this needle of length C up and down these parallel lines, yeah, we can see it's C over D. Now, if it is not perpendicular, we simply project it, again using trigonometry, to the perpendicular direction, because it is the perpendicular placement of the needle that determines whether it intersects with one of these lines or not. Moreover, if we're just tossing needles randomly, every angle is equally probable, right? So from elementary calculus, we can essentially compute that, well, the probability of crossing is essentially integrating over all possible needle angles. Here is 0 to pi. Between pi and 2 pi, it maps back to 0 to pi. Integrating this probability over 0 to pi, right? So there's a little typo here. And if we plug in this C times sine alpha over D over here, we get the expression down here. And notice that, well, C over D is constants. We're essentially integrating sine alpha over of D alpha over 0 to pi. We get this 2C over pi D, right? So it's easy to measure C and D, and then we get the estimate of pi. And also we can get, if you have taken fundamental statistics, you can get confidence intervals of your estimates and so on. So that's nice. And operationally, this is very easy to judge, a lot easier to judge than this casting dots method, right? Because it is easy to decide whether two line segments intersected or not, right? So it's less prone to human or like sampling or data reading error and so on. So this is to say, well, you may have encountered this in calculus and earlier, so sampling is a topic that goes back a long way. And the general motivation to doing sampling is that the distributions we encounter in real modeling tasks can be quite complex. Although this class have mostly so far focused on distributions that we can somehow reason about analytically, a lot of times it's not the case, right? And even in this class, we can see that posterior distributions can get quite complex. Mixture distributions can represent any distribution, right? And so this is also a plug of keep the content of this session in mind when we learn graphical models, right? So there's, well, I guess a spoiler is in the second section of graphical models, we're going to talk about Markov random fields, and then, for example, not learning the partition function or normalizing this probability distribution is actually a challenge. And in this session, we'll talk about some tricks to deal with that. So until then, right, the overarching goal of, say, tasks for sampling is to estimate the expectation of some function. under a distribution. These expectations can be posterior mean and variance and other moments and marginal mean and variance and so on and so forth. So the mental picture you can use to think about this task is there is some given function f drawn in blue of z, and we wish to evaluate what the expected value of it under a complex distribution. And here schematically throughout this class, it's drawn as a bimodal thing that may look like a two-component Gaussian mixtures, but maybe actually more complex, as we will see. So we've covered the motivation of why we would like to do sampling and what sampling looks like before computers and machine learning. Now we're going to talk about three bigger chunk, or essentially two bigger chunk of content. The first chunk is basic sampling algorithms. So given an arbitrary distribution, what do we do to generate a sample from it? And what do we do in cases where it's not easy to do so analytically? The first bullet is, okay, we do this typically. And then two methods for essentially sample from a complex distribution P of y from a simpler, let's say, Q of z, right? And it also motivates the next section, basically, what are the challenges of sampling from high dimensions, and also how do we explore the space of y, right? Okay. Or z. Right. Okay, let's do it. As we said, the overall goal is to estimate the expectation of some function. So assume we can sample from P of z. And it gives us, let's simply, okay, if we have z of small l, that goes from small l from 1 to big L somehow, and the IID of sampled from P of z, then the estimated expectation is simply like the unweighted sum of the function values evaluated at each of these samples. Okay, and the variance of this estimate is simply the empirical variance of these samples as well, right? Well, you can show that easily due to the linearity of summing and expectations that in the limit of infinite samples, right? The expectation of this sample f hat converges to the true expectation of the function e of f. So you will say, okay, that's simple. It goes nothing beyond what you already know in probability yet. And here we're just assuming we can draw samples. So the good news of this simple approach is there are also nice properties, right? So the accuracy of the estimator f hat does not depend on the dimensionality of z. This is a little bit counterintuitive because you are being warned about the curse of dimensionality all the time. Why there is no curse of dimensionality? So that's because fz is a scalar, right? And then P of z is the probability. It's also, well, let's write it the other way. We can, P of Z is also a scalar, and it's also non-negative. So we are essentially working in like a scalar space once we have f of z and p of z. That's nice. And another result is that the high accuracy or low variance of f, it may be achievable with a relatively small number of samples. The book threw out this magic number of like 10 to 20, but really what it is looking at is, well, once we're operating in the scalar space, and the big assumption here is assuming we can obtain IID samples from P of Z, then we really need a small number of samples. So you can reason about this using the central limit theorem. We won't go in there right now. So the literature in like theoretical properties of sampling is quite deep, right? So in this session, we're just going to essentially skim the surface, and we won't be able to go into many of the reasonings. But if you want more reading and so on, feel free to like look at the book or ask us. So there is the good, of course there's the bad, right? The hard thing actually, as we outlined here, is actually to obtain IID samples of P of Z, especially when P of Z is complex, is from high dimensions. So we said P of Z itself is not high dimensions, but the space of Z is high dimensions, right? So there is the notion of effective sample size. Basically, even if we have multiple samples of Z, as we will see towards the end of today's session, they may not be independent. And so the effective sample size is less. So there is actually a formula to calculate effective sample size if we use approaches like Markov chain Monte Carlo, which we won't give you in this lecture. But just keep in mind there is such a thing, right? And a lot of the algorithms we cover, it's harder to obtain independent samples as for reasons that we will still cover, right? So these are some of the drawbacks. So there is the good and bad, and you will ask, what's the ugly, right? So another concern is that f of z could be small in regions where PZ is large, and vice versa, right? And the expectation of f of z may be dominated by regions of small probability, implying that relatively large sample size, many samples, will be required to achieve sufficient accuracy. So the other concern, besides of P of z being independent, we would like to obtain samples where, like, when fz of z is large, these are the samples that will dominate the expectation term, right? When P of z is large, these are essentially high probability samples. So the accuracy of the estimate is the balancing force of the two. So these are the overall considerations that we'll revisit over the next hour or so. Let's talk about simple cases, right? So no, Buffon's needles don't readily cover an arbitrary f of z and p of z, right? So the simplest case is that, okay, what about p of z is 1 when z is in 0 and 1, right? So can we sample from that? Notice that we assume for this class that generating a random number like this is beyond the scope of machine learning. So this is, again, actually generating a uniformly distributed pseudo-random number is quite a deep topic, right? It requires, in a computer, you can write an algorithm that generates a sequence of numbers that approximates the property of random numbers, right? It needs to be mathematically very well crafted. Basically, the numbers need to be uncorrelated with each other, and also they need to like appear to be as close as possible, approximate the uniform distribution. So for those of you who remember hashing from intro to computer science classes, so that's one direction, right? So it has to do with large primes, and yeah, numbers appear like can be hashed to an like pseudo-random bucket. And if you don't, so the hashing like algorithm is also not perfect. So there are also ways to obtain pseudo-random numbers from things like atmospherical noise from the universe, right? So you can do that and use a web service to obtain your pseudo-random number. So for this session, we're going to just assume that someone has given us a sampling algorithm. So basically there is a rand function we can call that gives us a pseudo-random number from the uniform unit interval. All right. Hope that's makes you happy enough. So now the next step is, since we have this rand function, how do we sample an arbitrary low-dimensional distribution building on top of that, right? So the motivating question you can think about is, so how do we go from rand, the rand function numpy rand, to let's say numpy rand n function? Or it has the same name across many different programming languages. Basically, so it's how do we sample the standard normal, right? Okay, we'll get to that in a few minutes. Let's just first look at, again, this P of y, which is reasonably complex. Let's say this bimodal distribution. So recall from your probability class that one can do change of variable of probability distributions, right? And the formula works as follows. So basically, if like z is the uniformly distributed variable, and we can find essentially a y equals to a function form of z, then we can derive essentially p of y as p of z, which is constant in the unit on a unit interval, times the absolute value of the partial derivative of z given y, right? Right. So there's two conceptual gaps, right? One is how to get this one. The other one is how does an arbitrary random variable y relate to the uniform distributed random variable z, right? So both of these can be solved if we recall that the definition of the CDF, cumulative probability distribution function, is basically an integral of the density function y of like minus infinity up to the point of y that we're looking at, right? And we know that the CDF function sits between 0 and 1, right? And yeah, essentially like a uniform interval on the CDF function like this is like the probability that y lies in the appropriate inverse interval. So let's say median is here, and if we say cut it in quarters, then for example here, this will be the 25th percentile interval, and then the 15th percentile of y is here, right? So this is also to say that if we take the inverse function of the CDF, like basically the forward function of the CDF, h of y, maps y to z. And then the inverse function of h of y, right? So I'm just going to write it here. Y equals to h inverse of z, maps z back to y. So this is essentially what's written here. The steps for sampling a distribution P of y where we can get like analytical inverses or numerical inverses of its CDF, we simply generate a Z in the uniform interval, and then we use inverse CDF to obtain Y. So that's simple, right? So you can imagine you can do this to different functions, such as, like if, let's say, as a simple extension, we have this triangle-shaped Y between -1 and 1, then how do we sample P of y given Z, right? The extension to multiple variables is also along the same lines of thought. In here, we're just like the transformation to ideally multivariate uniform distribution where each dimensions are different is through this determinant of the Jacobian matrix. Well, again, partial derivatives. So here's an example. If we have an exponential distribution, if you look at Wikipedia, it will tell you that exponential distributions look like this. It's basically lambda times x power minus lambda y, and the shape is basically starts from some value and decays to 0 at the exponential rate for different like values of lambda. So smaller values of lambda meaning smaller decay, and larger values of lambda meaning faster decay. Okay, that's obvious enough, and y is positive. It's on the positive real line. Note that z is on the unit interval, but y is actually goes to infinity. So how do we make that happen, right? So we compute the CDF of y, which by integrating P of y, which leads to this analytical expression, 1 minus x of minus lambda y. So the lambda in front vanishes because of the integral. And then we can just solve this, right? The inverse of the CDF function is simply this expression. We do so, we can see so by, right, this becomes z. On the left-hand side, 1 minus z will give us x of minus lambda y. So we take the log and then divide the 1 minus lambda. So we get this expression. So that's easy. Yeah, and exponential distributions are quite important, right? For example, for those of you who have taken physics, you might have heard about Poisson distributions or stochastic processes. So there are things in real life where, for example, people arriving at bus stops or short noise arriving at your sensor are distributed according to exponential distribution in terms of the like how long they are between them, right? So being able to sample those is quite important. Okay, cool. So we said we're going to talk about the random number generator for Gaussians. So here it is. It's not as simple as the exponential distribution. And it requires us to move to 2D for a good reason. This method is called the Box-Muller method. So we first sample points. In here, we're assuming we have computers, and we can indeed sample points, dots inside a unit circle. Right, we basically sampled Z1 and Z2 on the unit interval, or actually unit interval, well, the interval between -1 and 1. We do this by simply scaling and shifting the original Z, right? That hopefully is easy. And then the probability of Z1 and Z2 inside the circle as we said is pi over 4, right? So in here we conditioned on Z1 and Z2 being inside the circle. They are uniformly distributed inside the circle. You can actually show this, we won't. So let's just assume now, after this, what's called a rejection step that we will talk about later, we have samples that are distributed uniformly inside a unit circle. And then the reason we need 2 dimensions is we're going to do need to do a transform to the polar coordinates, right? So the transformation as spelled out in the book is something like Z1 is R cosine theta, and then Z2 is R sine theta. For theta is between 0 and 2 pi. And R, the distance to origin is like between 0 and 1. Okay. So we won't do it in real time. It requires a few steps. This is actually covered in one of the exercises of the book with solutions posted online. Can go read about it. Basically, if you do this transformation, one thing you could see is that the probability is not dependent on theta, right? So theta vanishes and it becomes essentially the pi term, 2 pi term in front, the normalizer in front. And the transformation, the inverse transform of y involving Z1, Z2, and hence R and theta is as follows, right? So there's a term involving log of R, and then scale by Z1, you get Y1, and scale by Z2, you get Y2. Can also, so if we plug in this expression, we can see that and at the end, the probability becomes separable in Y1 and Y2. So we essentially get 2 IID Gaussian samples in this process. All right. So that's in a nutshell how we sample from distributions which we can derive analytical inverses in 1 or more dimensions. So back to this two-mode distribution kind of thing. Oh, okay. So yeah, thanks, Ella, who pointed to a quantum mechanics random number generator. We can use that, right? So a note about random number generator again. So if you're debugging machine learning code, you better use some deterministic random number generator with fixed seed, as you will do in assignment 2. Yes, if you are then sampling for like doing inference, like on your testing set and so on, then you can switch to a true random number generator where you cannot control the seed, but the randomness properties might be better. Yeah, thanks for that pointer. So the next approach we're going to cover is rejection sampling. So you say, what if P of Z is too complex? In here, we don't assume Z being the uniform variable again. So if P of Z is too complex and I can't really invert its CDF function, what can we do? One, I guess, natural thought is to say, can we sample from something else called Q of Z, which is easy, and we can analytically sample, and then build P of Z from there, right? And here we assume that sampling or inverse of H of Z is difficult, right? So basically H is hard. But then evaluating P of Z up to some unknown normalization is easy, right? So essentially, given the value of Z, we could output this. The next assumption is that we can draw samples from a simpler distribution. And we also assume that if we scale the simple distribution appropriately, it is a strict upper bound of P of Z. So let's assume that's the case. So the pictorial depiction is as follows. So K times Q of Z is like this blue envelope, and the red distribution sits strictly under it. Right. So if we do that, here's the same picture. So here's the steps, right? So we sample from this blue distribution. Suppose we get Z0, and that takes us here. We know that the Z0 is not from this red distribution, but we can actually evaluate, for example, how far away or how much more we are overestimating the probability of Z0 here. We just look at the relative height of the corresponding PDF or pseudo PDF, unnormalized PDFs in both cases, right? So we know that K times Q of Z is not normalized, and then P tilde of Z is also not normalized. So what we do, since we have this nice tool of the random number on the unit interval, so we generate that scale by K times Q of Z. We say that if this uniform random number is greater than P tilde of Z0, basically this region is, if U lies here, reject. If U0 lies here, then it's accept. We accept the sample. So we can show that by the same notion of sampling from the unit circle, that the remaining pair, right, the remaining samples are uniformly distributed under the curve of P tilde of Z. And in here, pairs refers to essentially Z and Z0 and P tilde 0. And if we normalize properly, then Z is distributed according to P of Z. All right, so here is rejection sampling, like a skeleton of how it works, right? So suppose we have a gamma distribution given in green, which looks like it has a bump. It has quite a non-trivial analytical form. You worked with this in your assignment 1, so hopefully you appreciate that. So we propose the proposal distribution Q of Z is Cauchy distribution, which is proportional to 1 over 1 plus y squared, or 1 plus 1 over z squared. So in order to scale Cauchy distribution to be an upper bound of the gamma distribution, we actually do this, right? So we use this expression where the z variable is scaled, well, shifted by c and scaled by b, and the constants b and k. What we do is that the inverse CDF of Cauchy is actually the tangent function. So we compute z from the uniform variable like this, and then we sample from Cauchy this expression, and we know that, well, for the gamma distribution, the CDF is hard, but we can evaluate this, right? Just plug in the gamma functions. So that will allow us to get a nice estimate of the gamma, or samples from the gamma, which are IID and nice. So you may say that, okay, this picture looks nice, but if my samples fall under these regions, yeah, they will be thrown away a lot, right? And we're wasting some samples if our samples fall into the reject region, right? So what to do about that? So the articulation of the general challenge is that we will want Q of Z to be an upper bound, or as it will be. The ideal case is that it's as similar as P of Z as possible. Otherwise, many samples are rejected. As you can see in this picture, if we mentally just take the outer product of this distribution and make it high dimensions, we can see that in high dimensions, the additional space outside of the support of P of Z is going to be quite big, right? So basically, the statement is in high dimensions, and in general, finding a Q of Z that is very close to P of Z is non-trivial. And finding a Q of Z that always upper bounds P of Z is non-trivial. Right, so like Q of Z has to be different from P of Z in order to become one of the easy functions, right? So this is an ideal that we can occasionally apply, but like in reality, lots of other issues come by. The book has another section on what's called adaptive rejection sampling. Basically, it bounds P of Z piecewise using simple functions such as lines. You can go read that. We're not going to cover it in detail. Instead, we're going to take our thinking to a slightly different direction, saying that instead of throwing away samples, can we just do a weighted sum of samples, right? So remember that in our desired scenario, we can do, our estimate of the value of f is a simple sum of f. So can we weight this, right? So another desired thought is basically rejection sampling has two levels of two sources of randomness, right? The one source is from the proposal distribution called Q of Z, right? And the other one is from the acceptance random variable U, right? You might think, right, so do we really need this, right? We started seeking one, can we get rid of this? One random variable, but now we're like essentially doing two levels of randomness. Can we be better? So we don't want to if we don't want to sample P of Z or accept or not of P of Z as an intermediate step, we wanted to come up with weights of the samples that are sensible, right? So the expectation of F is basically Fz weighted by P of Z, right? And we can trivially just plug in, well, multiply and divide by Q of Z, the proposal distribution at each point in Z, which will give us the following expression, right? So in here, we are instead estimating the, like if we treat Q of Z as the current distribution, right? Then we're estimating not the expectation of f of z, but the expectation of f of z weighted by the ratio between p and q, right? Right. So the advantage of this is that we make use of all samples. We waste no samples or reject no samples on areas where Q of Z, there's a lot of Q of Z, but not a lot of P of Z, right? And we also introduce these important weights that are the ratio of P over Q. Notice that these important weights does not necessarily have to be less than 1, strictly speaking, right? So this also alleviates the need to have Q of Z's that strictly upper bound P of Z, which is hard because these are probability distributions. If you make K too big, then it's upper bound, but there's wasted space. If K equals to 1, then Q of Z is not like, yeah, it's not upper bounding P everywhere, guaranteed. The requirement here, though, is basically when P of Z is greater than 0, then we want Q of Z is also greater than 0. Basically, the support of the Q of Z should be a superset of the support of P of Z. Right. So here's another thing we can use importance sampling for. It's basically if we can evaluate P and Q to some normalizing constant, as we will see over the next week for graphical model like distributions. This is quite a common phenomenon. Sometimes we know like the probability is bigger or smaller at the given value of, right? Because we know whether P of Z1 is greater than P of Z2, but we don't know exact values of P of Z, right? Z1 and P of Z2. So if this is the case, importance sampling can also help, right? So if we plug in the P tilde and Q tilde, which is the unnormalized version, well, to the expression we saw on the last page, we simply have them in front as the ratio of ZQ over ZP, right? So what the estimate, assuming there's a ZP and ZQ, then the estimate simply is revised as the weighted sum of f of the samples weighted by the same important weights that are now computed as the ratio of M normalized P over Q with the global weighting Z of Q over Z of P in front. So now we want to solve the question of estimating the ratio of the normalizing constants, which is still not the same as estimating normalizing constants themselves. Then the ratio, if we simply just plug in the definition of the normalizing constant, right? So ZP is basically the volume of P tilde of Z integrating or the domain of Z. So we plug that in, we get this. And then in the second step, we plug in essentially ZQ is a constant, right? So we plug in ZQ is Q of Z over Q tilde of Z, right? Into this expression, and we get this next term. Now what happened? So we know we have sampled Z according to QZ. And then the ratio of P tilde and Q tilde, they are the importance weights. So, okay, so now we get, the nice thing about this is that we get the importance weights for free. Meaning if we just sum over these importance weights without the Tiley function, take the average, we get the ratio of the normalizing constant. We are using the same samples. So that's neat. So is importance sampling essentially euphoria then? Does this solve all our problems? So the good thing here is that the importance weights R sub L corrects the bias introduced by sampling from a proposal distribution instead of the wanted distribution, and we don't need rejection. On the other hand, strictly speaking, it does not gain as much because when like RL is small, the weights will be small when the essentially the probability when the likelihood of accepting the sample is small. All right, so it's a different way of looking at things. And it works on unnormalized distributions, which is nice. Again, the success still depends on how well Q of Z approximate P of Z. And yeah, basically we want the support of Q of Z to be a superset of those in P of Z. We covered that. Moreover, the book has a few paragraphs discussing the pros and cons of these sampling approaches. I think it's informative that we read them to get a essentially high-level understanding. So what it says is, we talked about where the values of like regions of high and low values of P of Z and F of Z mismatch, we're in trouble. So that's still the case, right? So the apparent variance of even the importance weights. Now this is another random quantity in itself, and RL times of Z might be small, even though the estimate of the expectation might be severely wrong. So what this says is that if we use this procedure, it will produce a result. And then the result, the variance of the estimate might be arbitrarily big, but we don't know it. What we know is only like what the sample value is. So ideally, we also want, for example, Q of Z should not be small or zero in regions where P of Z are significant. Right, so like if RL is too small, right, so RL too big, it's bad. And in here, if RL is too small, then we're actually not getting lots of effective samples. These observations and concerns motivate us to look at the next series of sampling approaches. Okay, before I move to MCMC and Gibbs, is there questions about this first part of just sampling from a P of Z? Nope. Okay. Okay, people are all happy. Then let's talk about this another new class of method called Markov chain Monte Carlo. So the name, or short for MCMC. So the notion of, let's explain the name first, right? So Monte Carlo is basically a European town that's for gambling. That's known for. So we are sampling, essentially. That's what this part of the name says. And Markov chain, which we will go into more detail in a technical sense over the next little while, 15 minutes. The intuition is that we want to move towards high probability regions of P of Z. So, yeah, so instead of relying on, oh, sorry, don't need this. So, relying on some IID from Q tutor of Z, we wanted to essentially find a better value of Z in probability based on where we are, right? So, and we also hope that this new class of approach will scale better with the dimensionality of the sample space. If our goal is to sample from P of Z with some Z in RD, right? Then we would want to generate a sequence of Z, right? Where the new sample Z star is from, instead of Q of Z, now we evaluate conditional distribution of Q of Z, conditional current sample Z superscript L. And now the second step intuitively is we want to accept or reject the new sample. If it is intuitively better, like in probability, and then we accept the new sample and move to the next step. If it is not better, we actually treat the current sample, like we count the current sample again, right? So the high-level guarantee or the overall argument is that if we have appropriate schemes for accepting and rejecting samples, as L goes to infinity, Z of L approaches an independent sample of P of Z. Basically, we run this Markov chain sampling scheme sufficiently long, then that will give us a new independent sample of according to P of Z. So this is quite involved, right? So from a Q of, let's say, Z1, we actually use the notation here. We do P of Z1. Up until this point, we're saying, oh, we get a P of Z2 that's independent of Z1, right? And now we run this whole MCMC routine until sufficiently long, and then we get another sample. So in the beginning of this session, we said, well, we might need a few samples that are independent, and that's sufficient. So here's how you get the next independent sample. We can be more formal than that, right? So you, there are existing results on how do you compute the likelihood that you get an independent sample. It has some relation between the correlations of these different Zs in successive steps. We're not going to go into that. So let's look at a simple algorithm that's in the Markov chain Monte Carlo class called Metropolis. She's named after a person. So if we assume we choose what's called a symmetric proposal distribution, in here, well, proposal distributions in the last page, they are essentially Q of Z stars conditional ZL, right? It basically, it's the probability of moving to Z star from ZL. And now we require we'll talk about why symmetric later on, but right now we just assume we have a symmetric proposal distribution that has equal probability of moving from A to B and from B to A. Right, so in low dimensions, for example, Gaussians does that. Basically, if you have Gaussians centered on the conditioning variable, and any symmetric distributions will have that property. So normal distribution, let's draw a few things. So if we have proposal distributions like this, or like this, or a straight line like this, they're all kind of symmetric, right? And this is the ZL rather than 0, right? And we accept the new sample Z star with the probability that it's the minimum between 1 and the ratio of the two unnormalized probabilities P tilde. Right. What does this mean, right? So in plain English, the minimum of 1 and this ratio here basically means that we can implement this as a using a uniform random variable on the unit interval again. So because it's a probability, we don't want to be greater than 1. So basically, if P tilde of the new sample is greater or equal to the probability of the old sample, then accept. Otherwise, if this one is smaller, then we don't reject it right away. We accept according to what the random draw tells us, right? So intuitively, if the probability of the new sample is a lot smaller than the probability on the old sample, then we have a low ratio of acceptance. If they're close, then there's a decent ratio, like likelihood of accepting and moving to the new sample. And if we don't accept, then we keep the current sample and count it another time. So unlike rejection sampling, now if we reject the new sample, we set the current sample to the existing sample, essentially count it twice. So here's pictorially what's happening, right? Assume we sample from two-dimensional Gaussians, and the proposal distribution is isotropic Gaussians. Basically, proposal distribution, you can think of it like something like this, right? The equal probability contour is like this. We put a little circle around each sample, and then at each point, like we decide that we, for example, at this point, we actually first draw a sample according to the proposal distribution. It went there. That get rejected. Basically, the red paths between ZL and Z star are rejected. So therefore, we essentially come back where we retain this sample and count it once more, and then we jump to the next point, which is this green path or this green path. Because the proposal distribution is symmetric, from this picture alone, we don't know whether the path, well, it's a Markov chain, as we will cover in a little bit. All of the green segments, they encode a path of starting from somewhere. We can't quite see where it starts from. So it jumps among these green dots, right? So it's either gone here, or maybe it started from this point and then came here. Right, so we can essentially trace this green path with our pen leaving the screen here, right? And all of these red samples are discarded, therefore there is no outgoing path from this red samples. All right. Okay, so for those of you who have seen random walk probability, this looks like a random walk. So for those of you who haven't seen, just imagine a drunk person who takes a step forward or backwards at random. So in the disk, so assuming Z is in here, we assume Z is in some real space. And actually, converts integers. Here is the simplest Markov chain sampling algorithm, right? If we start from the origin, just imagine a drunk person starting from the origin, and it takes a step forward, let's say, to the positive direction with probability of a quarter, takes a step backward with a probability of a quarter, and then stays put, like in any given step, with half the probability. So we can easily verify that if the behavior is like this, the proposal distribution, basically this one, what we're written here is essentially P of Z star given Z of tau is like this. It's symmetric, right? In other words, no matter where you are on the integer line, your transition probabilities are the same, right? We can verify that if we start from the origin, the expectation of where you are at any given time is 0. You're equally likely to be on the positive and negative side, or side of the integer line. And the expected variance, or the variance of where you are, grows in time, but only as a function of the square root of the time that's elapsed. This is also not too hard to sort of to intuitively relate to, right? Because there is a non-trivial probability of staying put. And then once we move from the origin in one direction, it takes multiple coordinated moves in the single direction to actually be away from the origin. And once we take a step in the reverse direction, it will take us back, right? So we know that the expected absolute distance we are away from the origin is going to be smaller than linear in this case. And you can show, well-known results in Markov chains can show that the distance is on average is proportional to the square root of R. So what this means is that random walks are inefficient in exploring the state space. What this means is that we move away from the origin slowly, because imagine tau here is the number of samples we draw in the random walk, right? If we take 1,000,000 samples, we're only expected to explore the space roughly 1,000 in radius. So that's not great. So one overarching design goal of the Markov chain Monte Carlo algorithms is that we would like to somewhat be more efficient and deviate away from this phenomena, right? Okay. Now let's look at Markov chain a bit, and then we will introduce quantities that describe Markov chain to help us reason. Right. In fact, what we have talked about is I've given you a scheme to do sampling. We haven't shown that it's correct yet, right? Okay. We have about 15 to 20 minutes. So let's cover the I hope what you take away from here is one crucial intuition about Markov chain Monte Carlo. So here it is. So we can intuitively visualize this series of samples as a chain, right? Where in here, for example, in this random walk scenario, where I am next depend on the immediately previous sample, but it does not depend on all the other samples sort of that came before, right? And we can see the marginal probabilities of where I am next at the n+1 steps is, we can do so because of this, what's called Markov property here. This one is the Markov property, as we'll see in the sequential data section again. This is a simplifying assumption that will allow us to do many sequential modeling tasks sort of effectively or analytically, right? It does not necessarily hold true in real life, and whenever you can, you should test it. Because we're sampling here, we can prescribe that this is true, and that's okay. So because of Markov property, we're now essentially expanding using the Bayes rule of the marginal of P of Z of n+1 using Z of M, right? Assuming here is, we're doing this in a iterative algorithm, so we assume we already have marginal of Z of M1. So we're just now rewriting this probability of the next sample given the current one as the transition probability or transition kernel sometimes, or transition matrix if the sample space is discrete, right? And here we use subscript M in case the transition changes, right? So this is just the marginal probability we saw again. Here are some words or definitions that's helpful to precisely describe what's going on with a Markov chain. A Markov chain is called homogeneous if the transition probabilities are the same. So if we can drop the subscript M, that's nice. And the next set of words is the distribution is invariant or stationary if we can essentially drop the superscript M from the above equation as well. So that's nice, where we can essentially write P of Z instead of P of Z of n+1. So let's assume we have these. We would like to go after simple Markov chains that satisfy these two properties. In order for this homogeneous Markov chain to be stationary, or in like once we sample long enough, M large enough, we will want the sample distribution to be invariant, right? So it's invariant to M if after taking a step with this transition probability, then we're invariant, right? So there can be many transition probabilities that are invariant. So we can go and verify, for example, that random walk transition, like a step left, a step right, or stay put, is invariant. And trivial case is that if T is the identity matrix, then every distribution does not change, right? So this is the correctest argument of Markov chain Monte Carlo. Now here is another argument. So a sufficient condition for obtaining an invariant P of Z is what's called a detail balance condition, right? It says for every value of Z, right? For all value of Z, if it's not just a marginalization of prior, like the transition probabilities using transition, but if the product, this following product holds, then the distribution is also invariant. So the notation here has changed. So if we just plug in one equation to the next equations, then yeah, we could easily show that. So a Markov chain that respects this detail balance property is called reversible. So detail balance is quite an important notion in analyzing MCMC algorithms. For now, I would say, yeah, go verify it yourself and trust me that, yeah, detail balance is holds, right? So it's basically a product of the current distribution with the transition. Actually, it's the product of the distribution with the transition that leads to this distribution. Note that like the conditioning is basically we're conditioned on the first variable here. Yeah, so this is t of z. Right, we're conditioned on the first variable. So there's some notation. So, okay. So related to the notion of stationarity, a Markov chain is called ergodic if it converges to the invariant distribution, no matter with dot. Then the invariant distribution is called the equilibrium. It's easy to see that the ergodic Markov chain can only have one equilibrium, because if there is two, like it conflicts with, we can show by contradiction that it's no longer ergodic, right? So the trick then is for MCMCs is to choose the right transition distributions T to satisfy the detail balance property. So detail balance is a sufficient condition. If we don't satisfy this, we can still have a correct MCMC, but one easy way is to choose P so that detail balance is satisfied. So remember we talked about Metropolis, but didn't tell you exactly why it is correct. So here's the generalized version of Metropolis algorithm. It's called Metropolis Hastings, 2 people now. So remember in Metropolis, we want the proposal distribution to be symmetric. Now we relax that because now, yeah, so this one means T is symmetric. So if T is not strictly symmetric, we just need to revise the acceptance probability. The minimum between one part is the same. We want this to be a probability. The ratio of, we're essentially comparing the ratio of the current sample times where it's transitioning to going back from, so coming back from the Z star to Z tau, right? So roughly, this is like the top is Z star to Z tau. The bottom is, if we're at Z tau, how likely are we going to be in Z star? And the rationale of this acceptance probability is the same as what we said a few slides ago. If the top is larger, then accept. If the top is smaller, then accept. Still accept with a small probability. The rationale of not just rejecting samples that have a lower probability is as follows, right? You remember our stereotypical, say P of Z that we would like to sample may look like this. Then we would like to move essentially through this low probability region with non-zero probability to another mode, right? So the choice of proposal distributions, as you can see, is critical. It can allow us to move towards another mode or not. One common choice is, let's say, Gaussian, centered on the current state. So that's still symmetric, right? But it helps us to understand some intuition of this. The small variance, if the Gaussian has small variance, then we have higher acceptance rate. So we're likely to be moving in a high probability region, but slow walks through the state space because the next sample is going to be very close to the current one. Samples are not independent. If we do a large variance, you will have a high rejection rate, right? Okay, so graphically, this is what, let's say we're sampling for the same sort of two-dimensional non-isotropic Gaussian again with this red ellipses, right? And then if we're sampling using this proposed or transition distribution described by this blue circle as its variance, then we're essentially moving through this elongated mountain by random walk of size, this blue circle. And one argument that's pretty typical to MCMC, and we don't have time to cover why, is that the number of steps separating states that are approximately independent, basically when, like, how many steps do we need to get the next sample that's independent, is order of square of sigma max over sigma mean, right? Where sigma max is the larger standard deviation. So basically, if we're sampling a very elongated Gaussian, it's harder, right? Or let's roughly talk about why this works, right? Using the detail balance criteria. So the skeleton of the reasoning goes like this. If I were given the acceptance probability as this, the transition probability of the Markov chain is basically Q of K times the acceptance probability. We wanted to show that detail balance of P of Z times this transition equals to this inverse transition times P of Z prime. Well, plugging into plug T into this expression, we can show this by making use of the symmetry property of the minimum argument, right? So we won't do this. Feel free to do it offline. I wanted to say that what are non-trivial transition probabilities? So one intuition to jump between two modes that are actually quite far away from each other is that we can have the proposal probability or transition probability be a mixture between random walk and mode jumping. For example, if we do a mixture of a Gaussian with a small variance versus a large variance, we're shown to be like, and we do MCMC using this with this mixture model, we can see that we get samples from both modes. Otherwise, we just either keep jumping and rejecting or just move within one mode. Right? So that's very briefly what Markov chain Monte Carlo does. We're going to we have 3 minutes and we can talk about Gibbs sampling briefly. So Gibbs sampling is specifically a technique of MCMC that tackles high-dimensional joint distributions. Also, hint from next session onwards, we're going to be dealing with these joint distributions in graphical models, right? And now we're not treating Z as one unit for sampling, right? We are looking at individual components of Z, right? Instead of looking at P of Z, Z star given Z tau, we now look at P of part of Z, right? P of Z1 given, actually it's subscript now, Z1 given Z, Z2, Z3, and so on, right? So this is exactly what it does. So the overall goal is to do divide and conquer in high dimensions, right? So it also uses the same intuition of moving to the next sample condition on this current sample. So what it does, if we have, let's say, P of 3 variables, the joint probability of 3 variables, and assume we have an initial sample, what we do is that we generate the next sample of all 3 variables by conditioning on sampling in one dimensions and condition on all the other dimensions in turn, where we essentially partially update like the samples for each dimension conditioned on all the other dimensions. In here, since we have obtained, so we first obtain a new sample of Z1 conditioned on Z2 and Z3, and then since we have this new sample of Z1, we condition the next sample of Z2 on it and the old sample of Z3, and yeah, we basically rotate through the sample indexes like this. And we haven't talked about acceptance probabilities. Why is that, right? And why is this a good idea? Because here we are sampling conditioning on the exact condition distributions of a variable given everything else. P of Z is invariant, right? So by definition, each set step samples from actually P of one of the Z's conditioned on other Z's. As long as the current sample is drawn from correct distribution, the next one is too. As long as none of these condition distributions is 0 everywhere, it also satisfies ergodicity. And we can also show that the acceptance probability according to Metropolis Hastings is 1. So that's nice. So we're wasting no samples. Note here, we're kind of moving very slowly, right? In the high dimensions, we're not moving to the next point, but we're only moving to the next point in one of the dimensions. So here is a geometric illustration of what Gibbs sampling does. Basically, if we're sampling in 2D, we do coordinate-wise moving, right? And we always accept the next sample. Basically, starting from here, we first have a different Z2, and then have a different Z1, and then, yeah, we basically do this alternative move horizontally and vertically. And by the same argument of the Gaussian proposal in like non-isotropic Gaussians, the number of steps needed to obtain an independent sample is still like quadratic in the larger and smaller variance across the different dimensions. In here, the smaller variance is the conditional, the conditional variance of one variable with respect to another. So here is Gibbs sampling again, which is quite a ready-made recipe that you can apply if you would like to do inference in your high-dimensional graphical models. Okay, so that's that. So we basically covered sampling, why we do sampling, how can we do directly sample from one distribution, inversing PDFs, rejection, and importance weighting. We covered Markov chains and a few different flavors of it, Metropolis Hastings, and in particular Gibbs sampling. Is there any questions? Nope.
Are there any MCMC?
If no, then I will like end the recording of this and then talk about the video assignment.